This section explains why counting a material's large dimensions predicts its physics. Count the dimensions in which a material stays large and you have predicted its physics. That is the chapter's whole move. Shrink at least one dimension below, roughly 100 nanometers, and two things switch on together. The surface-to-volume ratio explodes, and the electrons, now confined, quantize, now confined, quantize. Siegel's classification simply counts the confined directions, 0 for dots and clusters, 1 for wires and tubes, 2 for sheets and films, 3 for nano-grained bulk. This count becomes the book's own skeleton, each dimensionality a later chapter. The introduction reads as an inventory of carbon nanotubes, graphene, and their composites. But the primitive that carries the whole argument is that the organizing axis is dimensionality of confinement, the count of directions, rather than chemistry. The fewer the free dimensions, the sharper the departure from the bulk. This part explains what makes a material behave at the nanoscale and why one number organizes the entire book. Shrink a solid until at least one dimension drops below about 100 nanometers, and its behavior stops being set by chemistry and starts by dimensionality. That count, 0, 1, 2, or 3 free directions, is the book's entire organizing axis, which is Siegel's classification. This opening chapter is its map. Every later chapter is its map. F. Later chapter is one row in a table indexed by dimensionality. The generative knob is the surface area to volume ratio. Confine a direction and that ratio explodes, forcing electrons into quantum confinement, turning bulk gold into something colored. Same element, fewer free dimensions, and the sharper the nanoscale effect. That monotonicity is why one-dimensional wires outshine two-dimensional sheets. From it you can predict every family of the chapters. This section lays out the single idea beneath the whole chapter. Nanoscience is a scale, not a material. Nanoscience is the regime, roughly 1 to 100 nanometers, at which a material's behavior stops following its bulk composition and starts following its size, shape, and surface. That is one regime rather than one substance. The chapter's move is to claim this regime is chemistry's native territory, not new ground. Chemistry, it says, is the ultimate nanotechnology, because chemists have always built matter atom by atom through bonds. That is sub-nanometer work, carried out, when needed, at megaton scale. So the generative primitive the book will exploit downstream is simple: control the bond, control the size, control the property. Everything after this, quantum dots, the dimensional classes from 0-dimensional through 3-dimensional, forces and self-assembly, instantiates one inversion. At the nanoscale, synthesis is design. This section explains how to read dimensionality at the nanoscale. The move is to count the directions that escape the nanoscale, the ones in which an electron still runs free, rather than the ones that reach it. A quantum dot pins all 3 directions below, about 100 nanometers. 0 survive, so it is 0-dimensional. A nanowire lets one direction run free. A sheet 2, bulk, all 3. Dimensionality is a confinement ledger, the number of directions in which an electron still moves as if the world were large. The chapter's real work is to install this single axis, 0-dimensional through 3-dimensional, as the spine the whole book hangs from. It also names the weak directional forces that self-assemble matter along each: hydrogen bonds, pi-pi stacking, and van der Waals. Shape follows. The count is what predicts the physics. This section explains why a carbon nanotube composite lives or dies by its interface, not its fiber. Roll a single graphene sheet into a tube and you get one of the stiffest fibers known. But strength in isolation buys nothing. The real claim of this chapter is a coupling law. A reinforced composite is only as strong as the interface transferring load from the matrix to the filler. The nanotube's intrinsic mechanics set a ceiling. The interface sets the floor, and the floor is what you actually get. So the whole arc, structure, then synthesis, then surface functionalization bends toward one problem, making chemically inert, hydrophobic tubes disperse and bond. The generative pattern is this. In any reinforced system, the limiting property is the weakest link in the load path, never the best number on the filler's spec sheet. This section explains the carbon nanotube as the one-dimensional rung of the book's dimensional ladder. A carbon nanotube is graphene rolled into a cylinder, one atomic sheet closed on itself and nested inside itself when the tube is multi-walled. The whole thread of the chapter is a single inversion. The spectacular intrinsic strength of the tube is not what you actually get. Bundle the tube into a matrix, and the composite is bounded by the interface, by where the force actually crosses from the matrix into the tube. Poor dispersion, weak bonding, and tangled clumps, and the load never transfers. The reinforcement sits there as inert cargo. So the engineering target migrates off the material and onto the boundary, functionalize the wall, disperse uniformly, bond well. The ingredient is already solved. The coupling is the problem. This is the one-dimensional entry in the book's dimensional ladder. This section explains why a single sheet of graphene behaves so differently from every other form of carbon. Start from one fact. A single carbon plane, one atom thick, means every atom is surface. Each one is accessible from both faces, with no interior to hide in. That lone fact generates the whole chapter. Buckyballs and nanotubes trap atoms on a closed shell. Flatten the sheet, and the bulk vanishes entirely, leaving pure interface. Composite gain follows mechanically. Mix a trace of graphene into epoxy and you match 10 times the mass of nanotubes because reinforcement scales with contact, and contact is now total. The same all-surface limit explains the rest, sensing, and single molecule. DNA read out through a nanopore, each a consequence of thinness pushed to its floor. Graphene is the book's two-dimensional extreme. It is the case where surface-to-volume ratio stops being a ratio and becomes the material itself. This section explains graphene as the two-dimensional body. Delete every dimension of a solid but two, and what remains is all surface, no interior for atoms to hide in. That is graphene. One carbon plane, each atom covalently bonded 3 ways with a 4th valence held in reserve, reachable from both faces at once. Every superlative the chapter piles on, strongest ever tested, more conductive than copper, thinner than paper, is one fact restated. A material with no bulk is nothing but its own interface, so all of it participates. And the sheet is generative. Roll it into the nanotube, stack it into graphite, so a single, two-dimensional object seeds the book's entire 0 to 3-dimensional hierarchy. This section introduces POS, polyhedral oligomeric silsesquioxane, the first of the chapter's structural primitives. Picture a silica cube about 1.5 nanometers across, with 8 silicon atoms fixed at its vertices. POS is a nanofiller that is a single molecule, where an ordinary filler is a fragment ground down from bulk material. That is the single molecule where an ordinary filler is a fragment ground down from bulk material. Because it is a molecule. Its size and geometry are set by chemistry. It is monodisperse by construction, and every corner carries a reactive group that you choose. So one scaffold becomes many materials by decorating its corners. Graft the cage onto a polymer chain, and the same object buys organosolubility, thermal stability, luminescence, plasticity, an oxygen barrier, even an anti-tumor agent. This is the chapter's exemplar of a zero-dimensional material, the filler you tune at the corner rather than in the bulk. You change a property by substituting the corner group rather than by milling the bulk. This part explains why BOSS earns its status as the canonical zero-dimensional nanomaterial. Picture a cube of silica, half a nanometer across, 8 silicon vertices, each one carrying an organic arm. This is the point where filler and molecule collapse into a single object, and that collapse is the whole thesis. Ordinary nanofillers agglomerate, seeding stress concentration weak points. Ordinary small molecules plasticize, softening whatever they enter. POS does neither because it disperses as discrete rigid cages at molecular scale. The inorganic core buys rigidity and thermal stability. You get reinforcement without the agglomeration penalty, and dissolution without the softening penalty. From here, you can predict the rest. Every property gain in the chapter is downstream of one structural fact. The reinforcing unit is a single molecule. This section explains what a zeolite fundamentally is and why a single structural choice generates all of its behavior. A zeolite is what its pores let through. Its function is its geometry. The shape of the pore is what acts, and the substance of the walls is almost incidental. Start by building a crystal from corner, sharing silicon oxide and aluminium oxide, tetrahedra, the SiO4 and AlO4 units. Each aluminium, 3+, that substitutes for a silicon, 4+, leaves the framework 1 charge short. So the lattice is permanently negative, and it cradles mobile, exchangeable cations. That single move generates everything. The negative walls screen guests by charge. The aperture size screens them by size, below 2 nanometers. The material is microporous, and it ranges up to macroporous. The result is a molecular sieve. You tune by adjusting the silicon to aluminium ratio rather than by changing the material. The chapter's whole arc hangs on one tension. The same cavities that make zeolites selective also trap bulky products and deactivate them. The composite is the repair for that self-inflicted limit. This section explains how a single atomic substitution turns an inert mineral into a functional, tunable material, the family known as zeolites. Start from a rigid, neutral lattice of corner-sharing silicon oxygen, tetrahedra, written SiO4. This is quartz, essentially inert. Now swap 1 silicon for aluminium. An aluminium 3+ ion standing where a silicon 4+ ion sat leaves the framework 1 charge short, and that fixed deficit must be balanced by a loose on sat leaves the framework 1 charge short, and that fixed decation lodged in a pore. This is the whole chapter. One substitution converts an inert scaffold into function. The silicon to aluminium ratio is the single knob. It sets charge density, and charge density fixes cation content, acid strength, thermal stability, and hydrophilicity all together. The periodic subnanometer pores then sieve guest molecules by shape. Everything catalogued downstream is that one defect, dialed, natural or synthetic, low silica or high silica, ion exchange, catalysis, and the composite fixes for overtrapping. This section explains a class of materials that are, at bottom, the cast of a void. Designed on purpose. A surfactant or block copolymer self assembles into my cells. The inorganic phase, silica or a metal oxide, condenses around them. Burn the template out, and what remains is ordered emptiness, channels from 2 to 50 nanometers across, whose diameter you tune by tuning the length of the template's tail. The pore is the active entity, and the wall is only its cast. Function comes from surface area and confinement, so what you engineer is the whole. That inverts once more for the nanocomposite. Refill the void with polymer or metal, and the confinement reshapes the guest, forcing extended chain crystals in ultra-high molecular weight that a bulk reactor never produces, and ultra-high molecular weight that a bulk reactor never produces. Templating the negative space and then exploiting it as a nanoreactor is the single move this section threads. This section explains how templating the void instead of the solid is the whole idea in a single arrow. Rather than build a framework and hope pores appear, you let surfactant molecules self-assemble into micelles, order them into liquid crystals, grow silica around that soft scaffold, then burn the scaffold out. The pore is the negative cast of the template. This lifts pore engineering out of the micropore regime, the world of zeolites, below 2 nanometers, built from single molecule templates, and up into the mesopore band, 2 to 50 nanometers. The generative primitive is the critical packing parameter. One amphiphile's geometry, its head area, its tail volume, its chain length already predicts the lattice, everything from spherical through lamellar. Molecular shape leads to supramolecular phase, leads to material void. Everything downstream, the surfactant charge, the hydrogen bonding, the calcination, is choosing which template. This section explains where the strength of living matter actually comes from. Strength in living matter is architectural. A tree's ability to carry its own weight comes from cellulose organized hierarchically, from the 1 nanometer fibril up to the meter-scale trunk, shown in Figure 8.1. No exceptional molecule is responsible. The strength lives in how one ordinary polymer is arranged across scales. The chapter's move follows from that. Nature already did the nanostructuring, so the strategy is to harvest its renewable polymers as ready-made nanoscale building blocks and recompose them into composites. Cellulose comes first, then chitosan, starch, and alginate. The property is inherited from the architecture rather than synthesized. The telos is substitution. Biodegradable, renewable, nanobiomaterials displace petrochemical polymers. The fear of fossil depletion is turned constructive, made into a reason to build. The quiet surprise is this. The hierarchy across scales that you extract from is the same hierarchy you must rebuild. The composite reprises the tree. This section states the single claim behind Chapter 8. Strength per weight in wood, bone, and silk is stored in how one molecule is stacked across scales, and not in the molecule itself. Chapter 8's thesis is that bio-based nanomaterials inherit their performance from hierarchy rather than from chemistry. The same beta-1,4 glucose chain becomes fibril, then microfibril, then cell wall, then growth ring, then tree. Figure 8.1 is the tree, anchor for this. This is the book's biological branch of its 0 to 3-dimensional survey. Where earlier chapters build nanostructure from the top down, nature's blocks arrive already organized and renewable: cellulose, then hemicellulose, then lignin, in that order of abundance. Read it as one claim. To replace petrochemical polymers, you copy the organizing principle across scales rather than the feedstock. Everything that follows, cellulose, chitosan, starch, is that same principle re-instanced. This section explains what a metal organic framework is and why it matters. Assemble a crystal from two chosen parts: metal ions as vertices, organic ligands as edges. The lattice that results is porous by construction, its cavity size and chemistry fixed at the drawing board rather than discovered. That is the whole move. A MOF's property is a function of its two inputs, so the same recipe generates an entire family by swapping the node or the linker. This was Yagi and Lee's founding insight. Everything downstream follows. Exceptional surface area and tunable pores make them gas stores and separators, sensors, catalytic hosts. The composites merely graft this designable scaffold onto a second matrix, a polymer, silica, or graphene, to borrow a property the framework lacks. Designability itself is what the chapter is for, more than any single material it produces. This section explains a class of material you author rather than find. Choose a metal ion for the node, an organic linker for the strut, and a periodic scaffold self-assembles, with its pore geometry fixed by that choice. Swap either part and porosity, sorption chemistry, and function all retune. The property becomes a function of its components, rather than a discovered substance. That reticular move places metal organic frameworks at the combinatorial limit of the book's material arc. The chapter's real thesis, though, is the composite. Raw metal organic framework is a fragile, humidity-shy powder, so you disperse it as the active phase inside a robust continuous matrix, a polymer, silica, or graphite oxide. The two phases then split the labor, function on one side and handling on the other. Neither, surrendering what it does. This section explains what unifies the 10 methods for predicting the stiffness of a polymer carbon nanotube composite. They form one ladder indexed by scale. At the bottom, you resolve the material as discrete atoms, molecular dynamics, which integrates Newton's law over interacting atoms. At the top, you resolve it as a continuous stiff medium, Halpern-Tsai, Mori-Tanaka, and finite elements, all elements. Multi-scale methods bridge the middle. You climb to the coarsest rung, whose length scale and time scale you can afford, trading atomistic fidelity for reach. Every rung estimates the same scalar, the effective stiffness, so what moves that number is invariant across all 10 methods: aspect ratio, waviness, orientation, dispersion, and above all, the transfer of load across the polymer carbon nanotube interface. The method is only a lens. The physics it must not blur is interfacial coupling. This section explains how one chapter predicts a single number, the stiffness of a composite, by choosing where along a single axis you model it. That axis runs from the discrete to the continuous, and the prediction depends only on where on it you stand. At 10 to the negative 10th power meters, atoms obey Newton's law that force equals mass times acceleration, which is the regime of molecular dynamics. At 10 to the negative 6th power meters, a continuum with perfect load transfer does the work, the regime of finite elements, and of the Halpern-Tsai and Mori-Tanaka models. Multi-scale methods is stitch the middle together. Here's the step that makes the whole scheme cohere. The method ladder is indexed by scale alone. The physics does not change from rung to rung. Coarsen the atoms and they simply become averaged phases. Every rung is the same function of the same 4 filler descriptors: aspect ratio, volume fraction, orientation, and interface quality. Aspect ratio dominates. A long nanotube stiffens the composite, while a short one at a poor interface can soften it. Amid a book that makes and measures materials, this chapter alone predicts a property before any synthesis is done. This section explains why the plant cell wall is already the nanocomposite you are trying to build, and how the whole program of the chapter is stealing its blueprint. Cellulose crystallites are the reinforcing rods. Lignin is the rigid matrix that locks them. Hemicellulose is the coupling agent binding the two, and abundance ranks them in that same order. The generative move is that strength lives in the crystalline domain, so isolate it. Hydrolyze away the disordered regions, and what remains is the cellulose nanocrystal, a defect pore whisker of 3 to 30 nanometers whose intrinsic stiffness rivals engineered fillers. Reinforcement then costs no petrochemistry. The feedstock is renewable and biodegradable. Predict the rest from this. Any structural biopolymer is a candidate once you can extract its ordered phase and disperse it in a host. This section explains how one chapter harvests a nanocomposite instead of building one. The plant cell wall is already a nanocomposite. This chapter's move is to harvest it rather than synthesize. 1. Cellulose, hemicellulose, and lignin, the wall's stiff fibril, its glue, and its aromatic filler are pried apart and redeployed as reinforcement inside synthetic polymer matrices. The generative primitive is top-down over bottom-up. The nanoscaled crystalline microfibril is liberated by stripping biomass down to the structure that biosynthesis already optimized, rather than assembled atom by atom. Everything downstream, biodegradability, strength, and biocompatibility, strength, and biocompatibility follows from that provenance. The chapter's place in the book is the renewable feedstock counterpoint to the engineered nanomaterials of the neighboring chapters. The nanotubes, the graphene, and the metal organic frameworks. Same reinforcement logic, opposite origin.